Okay, pre-cal students, in this video we will be looking quickly at the explanation of the characteristics of inverse trig functions. Now I'm going to give you a lot of information today that you will not need to write down, but I still want you to see it and understand what we're talking about when we talk about inverse trig functions. Your heading today, please copy this in your notes, is characteristics of inverse trig functions. Characteristics of inverse trig functions. Please also include today's date. Alright, let's continue on. Let's quickly review some Algebra 2 information. Please remember, you should have learned this from Algebra 2, not every function has an inverse function. Now if you want to take notes on what I'm about ready to show you right now, you're welcome to do that, but you don't have to. I just want to very quickly refresh your memory and show you what I'm talking about, okay? This is a function, and if you'll think of what you learned in Algebra 2, we learned that you can test a graph to see if it represents a function by using the vertical line test. And every vertical line that you draw on this parabola is only going to cross the graph one time. And so based on the vertical line test, this graph does represent a function. But now if we draw quickly the inverse graph, remember how to do that? You take ordered pairs and you flip them. So if I have negative 5, 5, over here then I would have 5, negative 5. And again, if you're a little lost, just watch. Okay, this is from Algebra 2, and you might not remember this, but I just want to show something to you that's a foundation for understanding inverse trig functions. Well, this graph here has negative 4, 1, so I'm going to put 1, negative 4. And then we have negative 2, 0, so I'm going to use 0, negative 2 for a point. And then we have 0, 1, so I'm going to use 1, 0. And then over here we have 1, 5, so I'm going to use 5, 1. And so by taking all of these ordered pairs and flipping them or swapping places with the x and the y, I come up with the inverse graph of this graph here. But notice something about this inverse graph. Does this graph represent a function? Well, no, it can't. Think of the vertical line test. Is there anywhere you can draw a vertical line that crosses this graph in more than one place? Well, sure. If I draw a vertical line here, it touches the graph in two places. Here, vertical line. Here, vertical line. If there's only one vertical line that intersects the graph in more than one place, then immediately the graph fails and it's not a function. We've got plenty of vertical lines that do that, so this graph is not a function. So let me ask a question. Does this function here have an inverse function? No. It has an inverse graph, but this graph is not a function, okay, because the vertical line test fails. Does this inverse graph right here have an inverse graph? Yes, it does. The inverse graph of this graph right here is this graph here. However, it is not a function. Understand that, okay? So this is a function here. This is not. So every function does not have an inverse function. Understand that, okay? Now let's apply this same thinking to the graphs of sine, cosine, and tangent, okay? And you don't need to take notes on this, just watch, okay? I will tell you when you need to take notes. Okay, we learned this in the past. Here is a graph of the equation y equals sine x. Okay, so there's the graph. Now, if I were to take all of these points and swap the x's and the y's like I did back here when I got this graph right here, if I were to do that, trust me, it would look like this. It would just be flipped. Okay, and so here's your sine function graph, and you don't need to take notes on any of this. Just listen. Here's your sine y equals sine x graph. The inverse of this graph is this right here. Now I have a question for you. is this graph here a function? No, it is not. Think of the vertical line test. I can draw a vertical line right here, and does it intercept the graph in more than one place? Yeah, it intersects it in, my goodness, 1, 2, 3, 4, 5 places. So this is not a function. Okay, this inverse graph of this graph right here is not a function. All right, now this is a function. Every vertical line I draw here is only going to touch the graph in one place, okay? But this is not a function. So here's what mathematicians did. They limited, now get ready to take some notes, okay? They limited the part of the sine graph from here to here. So when we're dealing with the inverse sine function, we're dealing with only this part of the graph. Now you don't need to write that down yet, okay? I'll tell you when you need to take notes, but we're getting really close to taking notes, so get ready, okay? Hopefully you've been awake and not sleeping, all right? I'm just trying to show you why we only use this part of the inverse sine graph, because we want a part that's a function. And now if this is all that I worry about is this green part, well, this green part is a function, because no matter where I draw a vertical line, it's only going to cross the green part one time. So by definition, when we say the inverse sine function, we're referring to this little part of the graph here. So are you ready? Please look at the domain. Now we're talking about the inverse sine graph, or the inverse sine function, okay? So write that in your notes, the inverse sine function. Write that down, okay? And here are some characteristics you need to know. First of all, look at the domain. The domain is how far it goes from the right to the left. Now let me go ahead and get rid of something. I really think I should do this. Remember, we're only looking at the green part of the graph, okay? So I want to get rid of this red part. We're only looking at the green part. When we're dealing with the inverse sine function, we're only dealing with the green part, okay? So there we go. Now, if you'll look at that, what is the domain? Well, the domain deals with the x values, and the x value, it looks like it goes from here and it goes over here. Well, if you'll look, students, that means it goes from, look, -1 over to +1, because the graph stops here and the graph stops here. So the domain goes from -1 to 1. You need to know that. Copy that in your notes. That's one of the things that you need to write down. And it is inclusive, so you would use brackets. So the domain goes from -1, comma 1. Now look at the range. Well, the graph stops right here, so it crosses, if you drew a line across the top and a line across the bottom, let me get a drink here real quick, you will then see how high and how low the graph goes. It looks like to me the graph goes as high as pi over 2 or 90, and as low as -pi over 2 or 90. So you could say the range, the y values, you could say inclusive, it goes from -90 to 90, or if you wanted to use radians, you would say -pi over 2 to pi over 2. So there's the range. Now let's talk about the quadrants. This is very important. So you should have written this down, and you should have written this down. You need to know the domain and the range. Very important. Now, the quadrants. Let's talk about the quadrants. Anytime we're dealing with the inverse sine function or an inverse sine problem, this is very important. The quadrants we're dealing with are quadrants 1 and 4. And can I show you why? Look, we know we're going from -90 to 90. So from here to here is 90, and from here to here going down is -90. So whenever we're dealing with inverse sine problems, which we're going to do later in another video, never forget this. Inverse sine functions deal with the first and fourth quadrants only. We don't use the second quadrant and we don't use the third. And again, that's because of the binding or the bounding, whatever, that we did. We put limits on this graph right here, okay? All right. Now, what are different ways to write inverse sine? Well, I'm glad that you asked. One way is arc sine. Arc sine means inverse sine, okay? So the graph right here, you could say y equals the arc sine of x, okay? Another way to write the inverse sine function would be x equals sine of y. Notice you're used to y equals sine of x. Well, we flip-flop the y and the x, and we put x equals sine y. These are two different ways that you could represent this graph over here, okay? All right, so please make sure you have all this information written down over here, numbers 1 through 4. Now, you do not need to copy down this graph, just sit back and listen. Here is your normal cosine function graph, okay? If I were to draw the inverse graph of this, it would look like this. And notice once again, I don't have a function. The vertical line test fails. It's not a very good vertical line, but you get the point. If I were to draw a vertical line like this, notice it touches the graph in 1, 2, 3, 4 places, okay? And so this graph is not a function. Now this graph over here is a function. I don't care how many vertical lines you draw, every vertical line you draw is only going to intersect the graph in one place, okay? So, because this graph right here is not a function, here we go again, mathematicians are taking only part of this graph, and they're taking the part from here to here, right there, okay? And by taking that part only, they now have a function. So I'm going to quickly get rid of this blue part of the graph. We don't need it. No need for it to confuse us, okay? So again, because we did not have a function, when we drew the inverse graph, we did not have a function. We're going to take just part of it, and that's the part we're going to use. Now, I don't care where you draw a vertical line. All vertical lines will only cross this graph one time. So because we have put limits or boundaries on the inverse cosine function, or the inverse cosine, we can now call it a function, okay? So here we go. Let's first of all look at the domain, okay? Let's take a look at the domain of this graph. The domain would be your x values. So it goes from here, -1, all the way to here, +1. So the graph runs from -1 to +1 on the x-axis. So your domain would be -1 to 1. Now your range, if you drew a line through the height of the graph and then drew a line through the bottom of the graph, it looks like to me it runs from 0 all the way up to pi, or 180. So the range is going to run from 0 all the way up to pi, or 180. So we would say the range is 0 to 180 degrees. Or if you wanted to use radians, you would say 0 radians to pi radians, okay? Now the quadrants. The quadrants are really important. Anytime we are dealing with an inverse cosine problem, the two quadrants you're always going to deal with are quadrants 1 and 2. You will not use quadrants 3 and 4. And by the way, doesn't that make sense? Look at your range. Your range goes from 0 to 180. And that's what these two quadrants do. From here to here, all the way over is 0 to 180. Okay? Now, I did type this incorrectly. This should say y equals arc cosine of x. And this should say x equals cosine of y. There we go. But these are the different ways that you could write the equation for this graph over here. When we're dealing with inverse cosine functions, we can say arc cosine. Okay, that's the same thing as saying inverse cosine. Alright, so y equals arc cosine of x, or we could say x equals cosine of y, which of course you're used to y equals cosine x, but now we flip the x and the y, and by flipping the x and the y, we now have an inverse equation. Okay? And we do have an inverse function because we put boundaries on the inverse graph. Okay? Alright, so what you need to be familiar with is all this information over here. You might be a little confused and not quite understanding where I'm getting all of this, but anyone can memorize this and make note of this, okay, so you can study it later. Okay, lastly, let's look at the tangent graph. And so here is the tangent graph. We've had this in your notes before. Hopefully you remember that. And there's the tangent graph, okay? And, notice no matter where you draw a vertical line, it should only cross the graph in one place. Okay, so this graph here does represent a function. Any vertical line that you draw will cross the graph in one place. Now, if you take this graph and you draw the inverse graph, it would look like this. And notice, of course, that if I draw vertical lines, then I don't have a function, because these vertical lines that I'm drawing are intersecting the graph in more than one place. So again, we had to put boundaries on the inverse graph so that we could have an inverse function. Okay, and so what we do is we're not going to use this, and we're not going to use this. Okay, so we're gonna bind ourselves. We're going to put boundaries to this part right here. Okay, so looking at that, let's go ahead now, excuse me, looking at this, let's go ahead now and talk about the domain, the range, the quadrants, and also how to write inverse tangent. This should have an arrow on it, and this should too. Okay? And so the domain deals with the x values. And the domain would continue. If you'll look, there's no boundary here, so it continues going on and on to the right, and it continues going on and on to the left. It's never going to stop. And so the domain is going to be parentheses, negative infinity, all the way to positive infinity, parentheses. In other words, it doesn't stop. Now the range deals with the y-axis, and notice the height of this graph goes to pi over 2. And the bottom goes to negative pi over 2. Now, I want to show you something that's a little confusing, but for the range, you would use parentheses, not brackets, because the graph is getting closer and closer to this dotted line right here, but it's never going to touch the dotted line. So pi over 2 is non-inclusive. It's not part of the graph. Same thing with this. The graph as it goes down is getting closer and closer to negative pi over 2, but it's never touching this line. Thus, negative pi over 2 is non-inclusive. It's not part of your graph. So because it's not part of your graph, you use parentheses, not brackets, okay? And it looks like to me the range would go from negative pi over 2, or negative 90, to pi over 2, or 90 degrees, because the height of the graph is going up to pi over 2, and the depth, or the lowest part of the graph, would be negative pi over 2. So that would be your range. Now the quadrants, okay, think about this for a second. I mean, if you know that your range goes from negative pi over 2 to pi over 2, then our quadrants are pretty obvious. We're going to use quadrants 1 and quadrants 4, just like we did also for our cosine. Excuse me. Like we did also for our sine function. If you look back in your notes very quickly to your inverse sine notes right here, notice the range went from negative pi over 2 to pi over 2, and we dealt with quadrants 1 and 4. Same thing here. Your range is from negative pi over 2 to pi over 2, so we're going to deal, whenever you're dealing with an inverse tangent problem, you're going to be dealing with quadrants 1 and 4, not quadrant 2 and not quadrant 3. Okay? So make sure you take notes on that. Make sure you understand it. I feel like right now this will be very confusing, but later on when we start applying this to inverse problems, you will understand why these quadrants are so important. And then here I have a typo again. It should be y equals arc tangent of x, and x equals the tangent of y. This would be two different ways that you could symbolize this graph right here, okay? Arctangent means the inverse of tangent. Okay, so y equals arctangent of x, or you could say x equals the tangent of y. Okay, so the main information you need to know are these four numbers here for inverse tangent, these four numbers here for inverse cosine, and also these four numbers here for inverse sine. The graphs are not really there for you to be tested on. I just wanted you to see where the information was coming from. Okay, if you have any questions, don't hesitate to call or email.